Polymers play a crucial role in the fight against Covid-19, whether that's with protective PPE, vaccinations, or in drug delivery. In this video, I'm going to cover polymers used in PPE, specifically the polymers used in one of the highest grade respiratory masks, the KN95. But first, let's cover the basics of polymers. Polymers are macromolecules that are made of small repeat units called monomers, and polymerization is the process by which small monomer units combine to produce a chain-like network called a polymer. There are a number of different ways of synthesizing polymers, but the two most common methods are chain growth and step growth. The KN95 is one of the best respiratory masks used in the fight against Covid-19, named for its ability to filter 95% or more of tiny 0.3 micrometer particles. But what makes this mask so effective? Let's take a look. The KN95 mask is made of 5 layers. From the outside working in, there's a polyester outer covering, then 2 layers of non-woven melt-blown polypropylene mixed with cotton. Following that is the electrostatic filter made of melt-blown polypropylene, and finally an inner layer of polycotton. The mask also has ear loops made of the polymer elastane. First, let's take a look at the outer layers, also known as the cover web. The cover web is made of a polymer called polyester. Polyester is able to maintain its shape. It is also strong and moisture resistant. These properties make it perfect for masks, as viruses contained within droplets of saliva or mucus won't be able to penetrate through the mask. Polyester is a synthetic polymer derived from products from the petroleum industry. Polyester is synthesized by step growth polymerization. This relies on 2 species with complementary reactivity. These are usually molecules with 2 functional groups at either end of the molecule. In this case, there's a dicarboxylic acid called benzene 1,4-dicarboxylic acid and a dialcohol called ethane 1,2-diol. In the presence of heat, the 2 monomers undergo a kind of nucleophilic substitution reaction with the elimination of water to create the repeat unit known as polyethylbenzene 1,4-dicarboxylate. These repeat units can react together in step growth polymerization. In this type of polymerization, monomers form dimers, then trimers, and these short chains can react together to make long chains. This is only possible because the monomers are multifunctional, hence both the monomers and polymers contain species that can react to form long polymer chains. Now let's move on to the polypropylene filter layers. This forms 2 layers of the mask. Polypropylene is made from the polymerization of propylene gas in the presence of a catalyst. This catalyst is known as the Ziegler-Natta catalyst. This process uses chain growth polymerization. This is where monomers are added one by one to the end of the growing polymer chain. Unlike in step growth polymerization, only the activated chains will grow, and the monomers themselves can't react together unless activated by the catalyst. The use of the Ziegler-Natta catalyst allows for high molecular weights, which means the polymer is made of many monomer units. These very long polymers can then undergo a process called melt blowing. In this process, the long polymer chains are blown out of a nozzle, pressed and melted together. This melt-blown polymer has a highly random arrangement of polymer chains, which enables for high particulate filtration. As the pores of the melt-blown polypropylene are random in size and no larger than 0.3 micrometers, and the droplets that contain Covid-19 are of the magnitude of 6 to 10 micrometers, polypropylene can successfully sieve contaminated droplets. Polypropylene fibres are often used as they have a low density, so are light, and it's hydrophobic, hence won't allow contaminated droplets of water to penetrate through the mask. Polypropylene may be mixed with cotton, as cotton will absorb moisture coming from the user of the mask. The next layer is the electrostatic filter layer. This too is made of polypropylene. This polypropylene layer again is made using a Ziegler-Natta catalyst, titanium trichloride aluminium diethyl chloride, but this time the catalyst is primed so that the isotactic polymer is formed. The isotactic form of polypropylene has all the functional groups on the same side of the polymer backbone, as opposed to the syndiotactic and atactic, where functional groups alternate and are in a random arrangement respectively. The benefit of the isotactic polypropylene is that when it's melt blown, it will form a highly crystalline structure. The more crystalline the better the polymer is at charge trapping the particulates. This means that it's easier to charge the polymer, hence it's better at trapping the particulates. The polymer is charged as it is fired through a charged needle onto a rotating metal surface in a process known as electrospinning. Alternatively, polypropylene could be sprayed with dimethyl dioxodecyl ammonium bromide in order to become charged. The final layer is called the shell. It's similar to the outer layer, however, it's made from polycotton, a mixture of polyester and cotton. This mix of polymers allows for the hot air exhaled by the user to be absorbed, making the skin dry and comfortable and preventing irritation. The last, but very integral part of the mask is the ear loops. These are made of elastane, which is a type of block copolymer. A block copolymer is a polymer in which different types of monomers are added to the chain in discrete sections. For example, monomer X is added first, then monomer Y, then monomer Z. Elastane uses two monomers called ethane 1,2-diol and diphenyl methane diisocyanate. The polymerization of elastane is another example of a step growth polymer. Sections of diphenyl methane diisocyanate provide rigid areas to the elastane, whilst ethane 1,2-diol provides soft, rubbery segments. This allows elastane to retain its shape after stretching, but it isn't too rigid so that it tears. That concludes the polymers used in the KN95. Although the KN95 has one of the best filtration rates of respiratory masks, it does have its drawbacks. Most of the monomers used to make the polymers come from unsustainable sources, primarily from the petroleum industry, which are quickly running out. Secondly, these masks aren't reusable, and the materials used don't readily degrade, as the majority of them are hydrophobic, hence have huge environmental impacts. However, advancements are being made in the area to make the masks reusable, including making the mask out of silicone and providing the filter layer at the front of the mask, reducing the amount of waste and unsustainable raw material used. But hopefully, sometime in the future, with the advancement of polymer science, we will be able to make sustainable, high quality, reusable respiratory masks. Thank you for watching.